Okay, so thanks everyone for tuning in. Today we are very happy to have Jon Sorce from Stanford, who's going to talk about the status update on tensor networks in quantum gravity. So
Great.
Jonathan, please take it away.
Yeah, thank you, Ignacio. So I would, of course, like to thank the organizers. I'd like to thank Ro for inviting me to give this talk, and Hugo and Ignacio for organizing. I want to give a little bit of a disclaimer, which is that I don't work very actively on tensor networks right now. This paper I'm going to be mostly talking about is about a year old, and I think that a lot of other authors have made very interesting developments in tensor networks in the interim. So that sort of inspires the title of this talk, the status update on tensor networks and quantum gravity. In addition to talking about the specific paper I was asked to talk about, I'm going to be talking about what I think are the most promising current directions for tensor networks and quantum gravity. And this isn't really an expert opinion, because like I said, I don't work very actively in this field, but it is, I guess, a collection of observations I've gathered over the past year. So for the talk itself, we're going to start with a review. And I know that there are probably many tensor network experts in the audience, but I did say in the abstract that I wouldn't assume a great deal of knowledge about tensor networks. So I'm going to talk a little bit generally about what we call the tensor network puzzle, or at least what I think of as being the tensor network puzzle, which is that in the past few years, various researchers noticed that these objects called tensor networks have many conceptual qualitative similarities with interesting properties of quantum gravity, holographic theories of quantum gravity. And the puzzle, as I see it, is and has always been, why is that the case? Why are these objects such good models for interesting features of quantum gravity? And then I'm going to be talking, and this will be the main body of the talk, about this paper I wrote about a year ago with Ning Bao, Jeff Pennington, and Aaron Wall, in which I think we provided a partial answer to that puzzle. And the answer is that geometric states in holographic theories of quantum gravity are tensor networks. And what I mean by that is that if you take any geometric state in a holographic theory of quantum gravity, then it is possible to write it approximately, to do a very good approximation of this state by a tensor network that faithfully represents the geometry of the state. And I'll explain all of the details of that as I go, but I think that gives us at least a partial answer as to why tensor networks are such good models. From there, we're going to spend, I think, a fair amount of time on Outlook. And the reason I want to spend so long on Outlook is because tensor networks have turned out to be a very good model for quantum gravity, but whenever we're working with a model, I think it's really important for us to very closely interrogate what are the questions that we can answer with that model and what are the questions that we can't. It's worth, remembering the theory we're really trying to learn about, which is quantum gravity, and figuring out sort of how far we can push the model. So I'm going to be asking a very general question, which is, what are tensor networks good for? What specific questions in quantum gravity can we expect tensor networks to be good models for? And similarly, when and how should we use them? I think that many authors in the past year have provided very interesting answers to this question. And I'm going to talk just a little bit about a short list of interesting problems, either open problems or recently solved problems, that I think tensor networks are very useful for. Okay, that's the overview of the talk. Barring any questions, I will get into the review. Okay, so like I said, I assume that many people in the audience are already familiar with tensor networks, so this is going to be a rather speedy review, but I think it's worth going over for everyone, in part just because tensor networks are kind of finicky objects. They admit many different descriptions. There are many different ways of thinking about them, so I want to stress the specific way of thinking about them that I'm going to be taking in this talk. Was there a question? Okay. So the basic idea of a tensor network is to take a quantum state and to somehow associate to it a geometry. Now, this is an idea that is very familiar to those of us who think about holographic theories of quantum gravity, right? In a holographic theory of quantum gravity, there are states that have these classical smooth geometries. There are states in the theory that correspond to what we would usually think of as a space-time. The idea of tensor networks is much more general. It says to any quantum state, we can associate a geometry. And the hope for those of us who are interested in quantum gravity would be that these two notions would somehow coincide, right? Would be to say, a tensor network is one way of associating a geometry to a state. Holographic theories of quantum gravity come with a built-in way of associating geometries to certain special states. And hopefully, when we apply tensor networks to those special states, we get some overlapping notion of geometry. So the goal is to associate to a quantum state a geometry. And one natural way to do that is to look at a circuit that prepares the state. So let me write this out explicitly. A tensor network, and this will be our preliminary definition, which we'll generalize momentarily, is a quantum state together with a circuit that prepares it. And when I say circuit, I mean this in sort of the quantum computing sense. I'll draw a picture which will make that apparent in a moment. But a quantum circuit is just, some initial state and then some sequence of unitaries that I apply to that state to get some different output state. So for example, let's say I start with some state psi, and let's say it's a state on a tripartite Hilbert space. Let's imagine it's a Hilbert space of 3 qubits, if we're, being good quantum information theorists. And then I'm going to apply a unitary A to the first qubit, apply the identity to the second qubit, and apply a unitary B to the third qubit. So this is an example of a quantum circuit, and it's also what I would call a tensor network for the state A, tensor the identity, tensor B, acting on psi. And the reason I say that this circuit has a geometry is because it does. It has some graph structure. It certainly has some graph topology. These different boxes that I've drawn act as vertices, and the wires of the circuit act as edges in the graph. And it actually has a geometry as well, which we'll talk about momentarily, which is that I can associate weights to each edge depending on the dimension of the Hilbert space that it's associated to. So in our field of quantum gravity, it's much more common to draw these tensor networks not as, left to right circuits, the way that information theorists think of them, but to draw them from sort of the center of a circle going towards the edge of the circle. And this is purely conceptual, but it gives us some very useful intuition, which is why I want to spend a second talking about it. So all I've done here is I've just, taken the picture that I drew above and I've bent the wires and I've drawn it differently. But already this picture gives us some intuition. It tells us that we should think of the state, the thing that is spit out by this circuit, as a boundary for which the circuit is the bulk. And heuristically, at least, this bears some qualitative similarities to, say, ADS-CFT, the state for which the tensor network is the bulk. Now, so far that's just, a very qualitative picture. It's just something that I've drawn. I've just taken a circuit and bent it around a little bit. We're going to talk momentarily about the very concrete connections between these two ideas. But first, I want to generalize our notion of a tensor network, because I think that by sort of drawing this circuit in this inward-outward picture rather than this left-to-right picture, we've liberated our minds in some sense from the confines of the circuit. Because what's important for this picture that we have here is not so much that this state was produced by a circuit, but rather that this state was produced by several components that I sort of fitted together in some modular way. So, for example, what's really crucial about this state is that I made it by taking some initial state psi, some unitary A, and some unitary B, and then fitting them together like Tinker Toys, in some particular way. So we would like to generalize our understanding of a tensor network to be any state that we can create by fitting together these Tinker Toys, even if it doesn't necessarily have a circuit structure, even if I can't necessarily write it as some sort of computational task where I start with a state and then at even time steps I apply unitaries and end up with something else. So this is going to be our generalization of a tensor network. This is going to be the most general thing that people call a tensor network. And it's going to be any state I can build with basic components. And the basic components are these things called tensors. So for the purposes of this talk, a tensor is just an object, T, that takes in some number of Hilbert spaces and spits out a state on some other Hilbert spaces. So it's an operator from some collective multipartite Hilbert space H in to some collective multipartite Hilbert space, H out. And furthermore, we demand that this object T is linear in each leg. That's just what it means for something to be a tensor. That's the familiar definition. There's also going to be an additional constraint that we usually impose on these tensors, which won't come up for most of the talk, but will come up at the very end when I talk about some other authors' work, which is that we usually want these tensors to be, if not unitary, then something like a unitary operator. So it's not always going to be possible for these T's to be unitary because, for example, I'm allowing the input Hilbert space and the output Hilbert space to have different dimensions. But it is possible to demand that the operator is what's called an isometry. An isometry just being an operator that is unitary onto its image. So we demand that either T or the adjoint is an isometry, depending on whether the input or output Hilbert space is bigger. If the Hilbert spaces are of different size, then only a map from the smaller Hilbert space into the bigger one can be an isometry. So that's just an aside. Let's look at some quick examples from the circuit that we drew above. One of the tensors in our circuit above was this unitary A, which was just a map from a single qubit Hilbert space to a single qubit Hilbert space. Another one of the tensors, which is perhaps the less familiar kind, was this state psi. And this is a tensor with 0 input legs and 3 output legs. And we can think of this as a map from, well, 0 input legs means I should just put in the trivial Hilbert space, which is just the complex numbers, mapping into the full 3-qubit Hilbert space, C2, tensor C2, tensor C2. It may be sort of unfamiliar to think of a state this way, but of course, any state in any Hilbert space we can think of as being a map from the complex numbers onto that Hilbert space. And that map is just the one induced by scalar multiplication of the state. I multiply any complex number by the state and I get a different state. Okay, so this is going to be our general definition of a tensor network, is that it's going to be anything built from these pieces. So it's anything built from tensors. And I stress that not every tensor network can be written as a circuit because of topological restrictions. So let me just write a very quick example, and then we'll be done with this review and we'll get into the main body of the talk, which is imagine, say, I have one tensor A, which takes in a state on Hilbert space 1 and spits out a state on Hilbert spaces 2 and 3. And suppose I have another tensor B, which takes in a state on Hilbert spaces, say, 2 and 3, and spits out a state on Hilbert spaces 1 and 4. Then I'm free to contract all of, output legs with corresponding input legs. So I can contract the 2s here, I can contract the 1s here, I can contract the 3s here, and I'm left with a tensor network, something I've gotten by slotting these tensors together, that gives me ultimately a map from the complex numbers to Hilbert space 4. In other words, a state on 4. So this is an example of a tensor network that if I were to specify the tensors A and B, would specify some state on Hilbert space 4. Okay, that's the basics of tensor networks. And I'm going to talk a little bit about their holographic properties before we get into the research portion of the talk. Are there any questions before I proceed? Okay, so the reason that people in our our line of work got so interested in tensor networks a few years ago, largely due to Brian Swingle, was because it became apparent that they have many holographic properties that are closely analogous to the properties of states in ADS-CFT. So let's say, for example, I draw a tensor network that looks like this. It has some interior legs. I won't draw the directions on those legs. And some exterior legs. So this is a tensor network that prepares some state. Now, already, this associates some topology to the state, and it's the discrete topology of the graph that the tensor network lives on. But it also has a geometry, and that geometry I get by weighting each edge by the log of the dimension of the corresponding Hilbert space. So each of these legs, right, represents a Hilbert space. In this above picture, the legs represented Hilbert spaces 1, 2, 3, and 4. So each one has a dimension, say, I'll just write some numbers here. Imagine those are the dimensions of the Hilbert space. We're going to assign a geometry to this graph by weighting each edge with the log of the dimension of the Hilbert space. The reason I choose the log of the dimension instead of the dimension is because I want the edge weights to be additive. That'll become apparent in a moment, but the dimension of a product of two Hilbert spaces is the product of the dimensions. But in our case, I would like the edge weights to be additive, so I take the logarithm. And that'll become, I guess, eminently apparent and interesting in a moment. So there's a fact, and this fact, as far as I know, was first noticed by Brian Swingle, which is that if I take, say, some subset of the sites on this boundary state, maybe I'll call that subset A, and I try to compute the entanglement entropy of A, it has an interesting bound based on any cut of the graph. So suppose I take some cut of the graph, which I've drawn here with a red dashed line. I'll call that cut gamma. And this is a cut that separates A from its complement on the boundary. Then it's always going to be true that this entanglement entropy is upper bounded by the log of the dimension of gamma. And this is where this logarithm shows up. This is why I wanted to weight the edges by the logarithm of the dimension. So this is quite similar to a very familiar fact to all of us, or to many of us, I believe, in holography, which is that this conjecture for Ryutake-Yanagi and its various generalizations tell us that the entanglement entropy of a boundary region in a holographic state is given exactly by the minimal area of surfaces dividing the boundary region from its complement, divided by an overall factor of 4G Newton. There are, of course, generalizations to this formula that I'm sure many of you are familiar with. It's not always a minimal surface. Sometimes it's an extremal surface or a so-called quantum extremal surface. I'm not going to deal with that subtlety at all. So this encourages us, at least conceptually, to think that in a tensor network, the log of the dimension of the Hilbert space corresponding to any cut plays something like the role of the area of a surface in a full smooth geometry in the holographic duality. So I want to emphasize that one of these is an inequality and one of these is an equality. So in the holographic case, we know that we can get the entanglement entropy of a region exactly by minimizing over all cuts. This isn't guaranteed in the tensor network case. The entanglement entropy is smaller than the area of the smallest cut, but it's not necessarily realized by any cut. However, there are very interesting cases, and I think these are the papers that really kicked off the tensor network research in earnest. There are interesting cases where this is exact, where the minimal cut of a tensor network does exactly give the entropy for the corresponding boundary region. And the
Jon,
first one, yes.
We have a question online.
Yes, go ahead.
So Deepak, if you want to ask a question, please unmute your mic and speak up.
Hi, yeah. This isn't really a question, more so as an observation, and I don't mean to interrupt the speaker's flow, but I just want to make a general note that what you're talking about are all facts that are very well known in a program of quantum gravity known as loop quantum gravity. And it's a 30-year-old program, and everything that, I mean, it's not to like say that what people are doing in tensor networks is not new. It absolutely is. But I find it interesting that, you know, it's almost like living in a parallel universe, because we have exactly the same structures. In fact, we have a geometric understanding of why areas are associated with edges, and it comes from, you know, canonical quantization of gravity. So it's, for us, it's not a mystery.
Okay.
I wanted to make this point.
Interesting. Thank you for that comment. I'm afraid I won't be able to address it in any detail because I have, you know, I'm about to move on from this subject, but thank you for bringing that up. Okay, so at least in the tensor network picture, there are interesting cases where this is exact, where the entropy is exactly realized by a minimum overcuts. And the first case that I think became, I mean, I'll call it revolutionary. I think this was a very big step in our understanding of tensor networks, was this happy network, which was a toy example, but was an example where these authors, happy are the initials of the authors, hence the happy network. It was this case where these authors constructed a specific tensor network that was sort of ADS-like. The graph had a hyperbolic geometry, much like, you know, ADS is a negatively curved geometry. And they found this network where the entropies of boundary regions were given exactly by minimal cuts throughout the body of the network. And then there was a case that followed this, which I think is kind of incredible that this works, which is the random tensor network. And I'll talk more about that at the end, because I think random tensor networks are one of the most promising open directions for tensor network research. So the idea of a random tensor network is I take some graph topology, and then I just put a random tensor on each site, right? Each of these white circles I've drawn here, I would put a random tensor on there. And random is drawn from some Haar random ensemble in a specific sense that you can look at the papers to understand. And then when I take the limit, as the dimensions of all the Hilbert spaces get very large, I find that I get this exact same behavior. I find that the entanglement entropies of regions on the boundary are exactly realized by minimal cuts to the network. So this is actually, I think, quite compelling, because a random tensor network is in some sense the most arbitrary thing we could imagine. We just take some graph and we put some random tensors on it and we get a state out of that. And it turns out that with a very high probability, that state has this interesting holographic property. So that's all I'm going to talk about review. I'm going to move on to the research part of the talk, talking about this paper with Ning and Jeff and Aaron. So perhaps I should pause now and ask if there are any questions about the review.
Can I ask a question?
Absolutely, yes.
So it's maybe an observation. So from the computational point of view, if the bound is not, let's say, how you say, fulfilled, then it means that you're using too large bond dimension for your tensor network. Because basically, the idea why we want to use tensor network is to simplify the description of the system.
Very good. Yeah.
Bond dimension is possible.
So, yeah, so this is a great observation, right? So Luca points out that we've sort of, you know, if we have a tensor network where this bound isn't realized, it means we've sort of made a mistake, because we are, in some sense, having bond dimensions that are too large, or that are larger than they need to be to accommodate all of the entropies in our state, right? We have some state, it has some entropies. Those entropies put a fundamental constraint on the bond dimensions that we can have in our tensor network, given by this inequality here. But if our bond dimensions are bigger, it means perhaps we've screwed up and we've made a tensor network that's bigger than it needs to be. Now, it is not always true that generic states admit tensor network descriptions, admit good tensor network descriptions that that have bond dimensions that exactly realize the entropy. And I think it is an important and interesting fact, and that's sort of the main content of the research paper I'm going to talk about today, that holographic states do have this property. They do have properties that allow you to build tensor networks that are as small as they can possibly be. Okay, any other questions before I proceed, or observations? That was a good observation. Thank you, Luca.
Yeah, I have a question.
Daniela has a question.
Yeah, thanks. Is there any work in which also the network structure, the combinatorial structure, is randomized?
Oh, yes, there is. I admit that I have not read it very closely. I think Xiaolang Qi thought about this quite a bit a few years ago. He and his collaborators looked at some random structure, and they put some vertices down, and then they did exactly what you're suggesting. They allowed some randomness in the adjacency matrix of the graph, so the topology itself was allowed to be somewhat random.
Can you say again the name of the author?
Xiaolang Qi. I'll put
okay.
it in the chat. Just name is in the chat. There's he and several other authors thought about this. I know that at least one of the papers has the phrase coherent tensor networks in the title.
Okay, thank you.
Yeah, although perhaps in that case they may have only been considering like quantum fluctuations in the geometry, not macroscopic combinatorial ones. I don't know the details very well, but that would be where to look. Okay, so the paper I'm going to be talking about is, the fundamental puzzle we have from all of these observations I've just made is why, right? Why is it that these tensor networks have these properties in common with quantum gravity? And perhaps the real answer is that quantum gravity really has a lot in common with tensor networks. That it's the other way around. So the paper I'm going to be talking about is one in which we found a concrete realization of this idea, where we showed that every state in a geometric theory of quantum gravity does have a tensor network representation that faithfully reproduces some aspects of its geometry. I'm going to work in a simplified case for convenience, and it's the case that I think we have the most rigorous basis for, although there's a lot of sort of, to my mind, interesting material in the paper that generalizes this. So let's consider a state psi, which is a geometric state. And for simplicity, we'll work in the ADS3 CFT2 correspondence. Okay, so that means that the fact that it's a geometric state means that it has some space-time picture associated with it, which is an asymptotically ADS3 space-time. And I'll draw some matter in the interior so you don't get fooled into thinking that it's the vacuum. This could be any space-time in asymptotically ADS3 boundary conditions. So if I look at any spatial slice of this geometry, then I can draw that as a two-dimensional Riemannian manifold with a circular boundary. And this is going to be the context that we work in largely for this talk. So if I look at some collection of boundary subregions on this time slice, say regions A, B, and C, then the Ryu-Takinagi formula suggests to us that their entropies are going to be computed by certain surfaces that are anchored on those regions. So for example, let's say a surface in 3 dimensions is just a geodesic, I should say. So for region A, perhaps it's this surface. For region B, perhaps it's this surface. For region C, perhaps it's this surface. But say I also want to think about the entropies, for example, of the union, A union B. And maybe the minimal surface for A union B is this one that connects the two. And then maybe I'll also think about the minimal surface for A union B union C, which is perhaps this one. Okay? So I have some, set of boundary regions whose entropies I am representing by surfaces. And the claim is that when I take any such collection, modulo one condition, I can construct a tensor network that reproduces those entropies faithfully. And let me just say exactly what I'm claiming. So given any set of boundary regions, like the ones I've described above, A, B, C, A union B, and A union B union C, provided that their minimal surfaces are non-intersecting, we talk about the case of intersecting minimal surfaces in the paper using some conjectures due to Takinagi and his collaborators, but the case that's on rigorous footing is the case of non-intersecting minimal surfaces. So given any set of boundary regions whose minimal surfaces are non-intersecting, there exists a tensor network for a state psi epsilon, which is very close to our original state psi, in a sense that I'll make precise later, whose bond dimensions are the right ones, whose dimensions are e to the area over 4g Newton, plus some subleading corrections. So let me draw that for this picture I drew here. Say these are the minimal surfaces that I'm trying to represent. Then I can draw a tensor network that looks like this. It has one edge for each of the minimal surfaces I'm trying to represent. And the bond dimensions, that is the Hilbert space dimensions associated to those edges, are the right ones to reproduce the geometry of the surface, at least to reproduce its area. And furthermore, this tensor network is going to approximately reproduce the state that I started with. So this is the main claim. This is, I think, a partial answer to why tensor networks are such faithful representations of interesting features of holographic quantum gravity. So I'm not actually going to talk in detail about this general case. What I am going to do is give you a complete description of the base case, which is where I have only one entropy that I'm trying to represent. So I have some state, and I partition the boundary into a region A and A complement, and it's a pure state, so their entropies are the same and represented by a single minimal surface that goes between the two. And I want to show you that it's possible to construct a tensor network like this, whose dimension here is e to the area over 4g Newton plus subleading corrections. And then you can produce a generic tensor network like the one I drew here by induction. Now, I want to pause before I actually give you the construction to sort of emphasize what this means. So or I guess what it should mean for us intuitively that it's possible to do such a tensor network description. So the state psi lives in this Hilbert space HA tensor HA complement. And that Hilbert space is huge. It's infinite dimensional even with a UV regulator, right? It's the Hilbert space of some UV regulated quantum field theory. Whereas the state that's produced by the tensor network, psi epsilon, is in a finite dimensional Hilbert space. It's in a Hilbert space of dimension e to the entropy times e to the entropy. Now the entropy can be quite big, but in a UV regulated theory, it is going to be finite. The entropy of either of these regions will be finite. So this tells us that this state that's in this huge infinite dimensional Hilbert space can be pretty well approximated on a finite dimensional Hilbert space, in particular on a Hilbert space whose dimension is given by the entropy. So I think that this is the core sort of conceptual result that we should take away from tensor networks and from the description I'm going to give you momentarily, which is that geometric states in quantum gravity can be simulated efficiently on finite dimensional Hilbert spaces, in particular on Hilbert spaces of size e to the entropy squared. This is what tensor networks really tell us about quantum gravity, is that we don't need the full Hilbert space. We only need a Hilbert space corresponding to the entropy. This process of simulating a state on a smaller Hilbert space often goes by the name of, or on a Hilbert space whose size is controlled by the entropy, often goes by the name of entanglement distillation. Now, if you look up the literature on entanglement distillation, you're not going to see it framed in this context. But it really is the same idea. This is fundamentally what people mean by entanglement distillation. There's more nuance to entanglement distillation, but this is what lies at the core of it. So let me talk a little bit about this idea before I talk about holography explicitly, this idea of simulating a state on a Hilbert space whose dimension is controlled by the entropy. So let's suppose I have some state on what I'll call a 2-qubit Hilbert space. So that's just 2 d-dimensional Hilbert spaces. And I'll call the first one A and the second one A complement, just to make contact with what we were talking about before. So there's a special kind of state on this Hilbert space, which is called a maximally entangled state, which is just any state that I get by summing over a complete orthonormal basis. There are many different states, they're non-unique. Any orthonormal basis is going to give me a different state of this type, but all of these states are what we call maximally entangled. And we call them maximally entangled. Well, for one thing, because they sort of exhaust entanglement in a complete basis, but also because their entropy on either of the subsystems is given by the log of the Hilbert space dimension, which is the maximal von Neumann entropy that you can have for any state on a Hilbert space. So the maximally entangled state, and the reason I write this out, even though I know maximally entangled states are sort of a very basic concept, is that I want to draw your attention to the fact that the maximally entangled state really needs the entire Hilbert space. It has maximal entropy, and it needs the entire Hilbert space because I need to sum over an entire basis, a basis of both of these subspaces in order to actually write the state. So the question is, if my entropy is submaximal for a different state, if I give you some state whose entropy is submaximal, do I need the entire Hilbert space to write it down? So given a state psi in this same Hilbert space, qdit tensor qdit, and suppose that its entropy is submaximal, so the entropy of a reduced state is equal to, say, log k, which is some number that is less than log d, the dimension that we started with. The question is, can we write psi as being very well approximated by some state that is on a subspace of size ck tensor ck? And the answer is no. The answer is no in general. This is not possible for many states. It is possible for holographic states, which I'll say momentarily. But the reason that this procedure, or this sort of question is interesting for quantum information theorists is because it's possible in this so-called asymptotic Iid limit. And the asymptotic Iid limit is just the limit where I take a large number of copies of any state. So I take psi, I tensor it with itself n times, and I take the limit as n goes to infinity. So in this limit, it is going to be possible for any state to do this thing that I do this procedure that I wrote here. It's going to be possible to write this asymptotic Iid state on a subspace, or to approximate it very well, on a subspace whose dimension is controlled by the entropy. And I would actually like to say that this is fundamentally the reason why the von Neumann entropy is an interesting quantity. Those of us who are quantum gravitational theorists, we became interested in the von Neumann entropy because it seemed to have this interesting geometric interpretation. The von Neumann entropy of a subregion is computed by the area of a surface in the geometric theory of quantum gravity. And I think for many of us, that was sort of enough reason to be interested in this quantity, the fact that it gave us some sort of geometric object that we could study. But for quantum information theorists, the reason that the von Neumann entropy is interesting is because in this limit where we take a large number of copies of a state, it helps us constrain that state. It helps us limit it and write it on a smaller Hilbert space. Fundamentally, that fact is behind the ubiquitous nature of the von Neumann entropy in quantum information theory. This is why it is so useful for constraining various operational tasks. And what I'm going to tell you is that this same feature, this subspace feature, is also possible for states in large N holography. And if you take nothing else away from this talk, I hope this is the thing you take away, that in holography, we don't have the luxury of taking a large number of copies of a state. We sort of work with single universes. We're not working in the same context that quantum information theorists work in. And yet the von Neumann entropy is a very interesting quantity to us. And I think that this is why. Everything I'm about to say is why the von Neumann entropy is so interesting and useful. It's because for a single copy of a holographic state, we obtain this same sort of subspace approximation feature that we get for the asymptotic Iid limit of a generic state. So in order to prove this for you in large N holography, I'm going to first need the notion of an entanglement spectrum. I'll just say what this is very quickly and draw some pictures that I think will be useful. So if you give me a state on this Hilbert space we've been considering, the 2-qubit Hilbert space, then I write its reduced density matrix on one of the subsystems in the usual way. And this density matrix is Hermitian. So it has real eigenvalues, which I'll call lambda I. And sort of crucially, because the state psi is pure, those eigenvalues are the same regardless of which Hilbert space I trace down to, whether I trace down to the left Hilbert space or the right Hilbert space. And the spectrum of the reduced density matrix is what we call the entanglement spectrum of the state psi. If I plot those eigenvalues, say in reducing order, perhaps I get something like this. So let's imagine that this, full sort of domain of the plot is the full d-dimensional Hilbert space. And I can look at, say, the first, the number of eigenvalues corresponding to a k-dimensional subspace. And what it would mean for a state to be distillable, what it would mean for a state to be faithfully representable on a k-dimensional subspace would mean that these eigenvalues outside of that little box I've drawn are very small. They don't particularly matter. They don't contribute much to the state. So I'm going to prove to you that that's true in holographic states using some various path integral methods. It's really a lot simpler than that. Okay, so before I continue and actually provide this proof for you, I would like to pause for any questions. Okay, if there are no questions, I will proceed.
Maybe I have a question, sorry.
Yes.
Shouldn't you also prove that the rest is flat?
It is. The rest is effectively flat. I decided not to talk about that in detail in this talk for time. I will tell you that proving that the rest is flat is not actually important for doing what I said I wanted to do, which is constructing some tensor network that has the right bond dimension. I don't actually need the rest of the entanglement structure to be flat. So what Luca is pointing out is that in entanglement distillation, this is what I referred to as the nuance of entanglement distillation. It's not just true that I can represent the state faithfully on some subspace, but that the state on that subspace is approximately maximally entangled, hence has a flat spectrum, like Luca was suggesting. It is true of the construction I'm about to do that you can show that that spectrum is approximately flat. If you pay close enough attention, I'm actually going to sort of, and maybe I'll say a few words about it when I get there. I am going to implicitly prove that, but it's not strictly important for the simple fact that I'm trying to prove. There's a lot of detail in the paper, if you're curious. Okay. So, in studying the yes,
I have a
go
question.
ahead, Mike.
I tried to go with the netiquette, but it didn't work. So
that's okay.
Shall I think of it as you having like two tensors? Like these tensors correspond, roughly speaking, to entanglement wedges. One for A, the other one for AC, and the summation corresponds to gluing them along the retoconnect surface. Like this is roughly speaking the idea.
Yeah. That's exactly right. Yeah, each tensor you should sort of imagine. When I talked at the very beginning about this sort of modular structure, we're going to find, and I mean, you see that explicitly in this picture I've drawn here. Each tensor corresponds to some entanglement wedge, and I glue them across the extremal surface that bounds the two different entanglement wedges. And that's what it means to slot these two tensors together. Now, of course, this tensor network picture is, it loses a lot of the structure of the space-time. I can, just slot these Hilbert spaces together. I don't actually need to worry about some geometric gluing. So it's a lot easier in that sense, but that is the intuition.
I see. And yeah, I mean, do you want to think of these tensors as somehow related to modular Hamiltonians for these subregions? Like it's, well, you're
actually
computing. Yeah.
I'm about to talk about modular Hamiltonians.
Okay.
I'm not sure if that has, if it's going to be exactly what you're thinking of, because I'm not going to talk about modular flow at all.
No, I was more thinking that like in tensor networks, like if you view them as numerical ansatz, like you have access to tensors, you can do like various things with these tensors, right? Like you can look how they act, like when you put something on one leg and so on and so forth, right? So I'm just wondering to what extent you get access to such considerations here.
Yeah, great. So that's a great question. I won't talk about that in the main body of the talk, but I will talk about that in the outlook at the end, because there are some interesting work that's been done in that direction. So perhaps I can defer that question.
Okay, thanks. Looking forward to it.
Okay, so we're studying the spectrum, the entanglement spectrum of these states. It turns out for our purposes, for it to be easier, it's easier not to work directly with the state itself, but with what we call the modular Hamiltonian, which is minus log of the state. So the density matrix is a positive operator, which means that its logarithm is a Hermitian operator. So we can think of this modular Hamiltonian, or so we can think of this object K as being a Hermitian operator and hence a Hamiltonian. Okay, so we're going to study the spectrum of the state by studying the spectrum of K, and we're going to try to show that that spectrum is tightly constrained. So there is a method for studying the spectrum of a Hamiltonian that those of us who were raised as physicists learned, perhaps in one of our early quantum mechanics class, which is that you can study the spectrum of a Hamiltonian by looking at its partition function. So the partition function of a Hamiltonian, right, z of beta equals trace of e to the minus beta k. If I know this function for all beta, then I know the full spectrum of the Hamiltonian. And I'll say that explicitly in a moment. I can write this trace as an integral. If I call the eigenvalues of the Hamiltonian E, and I integrate over the density of states of the Hamiltonian of e to the minus beta e, that's the same thing as the sort of trace expression that I've written above. But when I write this as an integral, I can actually see explicitly that this integral, what it does is it takes the Laplace transform of this function, the density of states. So I can invert that Laplace transform. If you're not familiar with Laplace transforms, don't worry too much. The details aren't important. I can invert that Laplace transform, and I do some contour integral of the partition function in the complex beta plane, and that gives me the density of states. So this is what people mean when they say that knowing the partition function of a Hamiltonian explicitly gives you a spectrum. You can take an inverse Laplace transform of the partition function. But what we're really going to be doing is trying to evaluate this integral, or at least put some constraints on this integral, in order to talk about the density of states for a holographic modular Hamiltonian. So the partition function z of beta, if I write it back in terms of the state that I started with, it's just trace of rho to the beta. And this object has a special name. It's called the beta matrix moment. And for holographic states, matrix moments have a very particular scaling. I'll explain this in a moment. But for holographic states, the beta matrix moment, trace of rho to the beta, always goes like e to some number over g Newton. That number is really a function, right? It depends on beta. And there may be some coefficient, doesn't really matter. But yeah, so this is the point, is that the matrix moments all scale in this way. And I'll give you some words that sort of prove why that's true, although I won't go into detail. But first, let me give you some intuition. The beta matrix moment shows up for information theorists most commonly in the definition of the Rényi entropies. So the definition of the Rényi entropies is this. Trace of rho to the beta is equal to e to the 1 minus beta times s of beta, which is the beta Rényi entropy. And this is just the definition. And the Rényi entropies generalize the von Neumann entropy. Thanks to Ryu and Taki Inagi, we know that in holography, von Neumann entropies go like 1 over g Newton. So it shouldn't be too much of a stretch for you to believe that the Rényi entropies go like 1 over g Newton as well, which is enough to establish the scaling that I claimed. For a little bit more rigor, and I'll say this very quickly, and some of you it will make sense, and for some of you it won't. A way to see that the scaling has to be true is that the beta matrix moment of a holographic state can be set up as a gravitational path integral calculation that is tractable in a saddle point analysis. And the saddle points of the Einstein gravity path integral all have action that scales like 1 over g Newton, which is why the path integral calculation that you do ends up giving a scaling like e to the some number over g Newton. Okay, those are all the words I'm going to say about it. This scaling is all that we'll really need. So we're going to use the scaling, and we're going to go back to our calculation of the density of states. Oh, I should say really quickly before I continue that a lot of what I'm talking about right now is adapted from unpublished work by Patrick Hayden, Brian Swingle, and Michael Walter. They made a lot of these observations in a slightly different context, and unfortunately never published the paper. But I would like to credit them with some of these ideas. Okay, so I'm trying to compute the density of states. And the way I do that is by taking the inverse Laplace transform of the matrix moments, which scale, as I claimed, like e to the sum number over g Newton. And because we are taking the holographic limit, because we are taking a limit where we take g Newton to be very small as compared to the radius of curvature of the spacetime, we can do a saddle point analysis of this integral. And we find that this whole thing is going to be equal to some other number, or really some function that depends on the product g Newton times the eigenvalue of the modular Hamiltonian over g Newton. This is very heuristic, but it's true. This is just a saddle point approximation for small g Newton. So what we've learned is that the density of states of the modular Hamiltonian of any holographic state looks like an exponential weighted by 1 over g Newton. And what that's going to mean in practice is that it itself has a saddle point, or integrals involving it will have a saddle point in the limit that g Newton goes to 0. And that's why, fundamentally, the spectrum, the entanglement spectrum of holographic states is so tightly constrained because of this saddle point property. So for example, let's say I want to compute the trace of the state. Okay, we already know the trace of the state. We know that the trace of the state is 1. But let's do this because it's a normalized state. But let's do this as an instructive sort of example, and it'll end up being very important. The trace of the state is computed in terms of the density of states by this integral, right? E to the minus e is just the eigenvalue of the state corresponding to the eigenvalue of the modular Hamiltonian. So all this integral does is it sums over the eigenvalues of the state. But because of our saddle point analysis, because we know that the density of states is given by some exponential in 1 over g Newton, we know that this is dominated by some saddle. And that saddle point I'm going to call E0. Okay? So what that means is that the trace, the fact that the trace is dominated by some saddle point, and the trace is just a sum over the eigenvalues, means that the eigenvalues are sort of dominated by some region of eigenvalue space, right? If there is a saddle point that effectively computes the sum over all of the eigenvalues, that means a lot of the eigenvalues have to be pretty small. Using standard estimates on saddle point approximations, we can see that if we throw out all of the eigenvalues outside of a certain range, and that range is going to be E0 plus or minus order 1 over g Newton log of 1 over epsilon. Epsilon is going to be some number that I can fix by hand. If we throw all of the eigenvalues outside of this region, then we're going to get a pretty good approximation to the integral that I wrote above within order epsilon. And, I fix epsilon. I fix epsilon in the eigenvalue range in order to give me the error that I want in this integral. So this tells us that I can throw out a huge number of the eigenvalues and still get a pretty good approximation to the trace, which means that all of the eigenvalues that I threw out collectively only sum to be something of order epsilon, which means that those eigenvalues are not especially significant for the actual physical properties of the state. They're very, very, very small. So what this tells us is that if I take a different state, psi epsilon, which is the state I get by throwing out the eigenvalues that I named and normalizing the state, so it's a normalized state again, this different state is going to be very close to the state that I started with. And the precise sense in which it's going to be very close is that the overlap between the two states is going to be very close to 1. And that means that they have very similar physical properties. For example, the expectation values of bounded observables are very tightly constrained. Okay? So what I'm going to claim for you is that this approximate state psi epsilon that I got by throwing out these non-saddle point eigenvalues is going to be a good tensor network for the original state, or is going to have a good tensor network description. So let me tell you briefly the properties of this state, psi epsilon. Well, we know its maximal and minimal eigenvalues, or the maximal and minimal values in its entanglement spectrum, because that's how we constructed the state, by throwing out certain eigenvalues. The maximal eigenvalue goes like e to the minus e naught plus order 1 over root g Newton, and the minimal eigenvalue goes like e to the minus e naught minus order 1 over root g Newton. And to answer a question that was asked before, possibly by Luca, these two lines are actually sufficient to show you that the spectrum of this state is essentially flat. I'm not going to talk about the details of that, but that's basically what's happening here, is that the spectrum is flat up to order 1 over root g Newton corrections. But for our purposes, what's important is that because the maximal and minimal eigenvalues are so tightly constrained, that constrains for us the rank of the state. That constrains for us how many total eigenvalues there can be. Because the state is normalized, you know, the sort of the product over, you know, basically if all of the eigenvalues were at the minimal eigenvalue, that would give me some constraint because they would have to sum to 1. If all of the eigenvalues were at the maximal eigenvalue, that would give me some constraint because they would have to sum to 1. So we can combine those to get some constraint on the rank of the state, which is e to the e naught minus order 1 over root g Newton. Okay, so we're very, very, very close to what we wanted. This state psi epsilon lives on some subspace whose rank is e to the e naught minus order 1 over root g Newton. All we need to do is tell you what that e naught is. And I think just sort of by looking at the picture, it shouldn't be too hard to convince yourself that that e naught is going to have to be the entropy of the state. But we can see that explicitly by showing that the entropy is computed by this integral over the modular Hamiltonian density of states. This integral that I've written here is just trace of rho log rho in modular Hamiltonian language. And if I do the saddle point analysis that I just described, then this is going to be dominated exactly by the saddle E naught. So that tells me that this E naught has to be equal to this sort of reduced entropy of the state. Okay, so here's our conclusion. Is that given a state psi, a holographic state in A tensor A complement, there exists some state psi epsilon in a smaller space, you know, of Hilbert space approximately e to the entropy times e to the entropy. You know, there's a subleading correction there, but I won't worry about that for right now. And when I include these smaller Hilbert spaces back into A tensor A complement, that state that I get is going to be very, very close to the original state psi. So this tells me that psi can be faithfully represented on a subspace of dimension e to the s, e to the s. And let me give these inclusion maps names for a moment. I'll call them, say, V and W. If I do that, then what I'm being explicitly told is that the state psi is very close to the state V tensor W acting on psi epsilon. And this expression is a tensor network. In particular, if I take this equation and I write it, or I draw it in tensor network language, this tells me that the state psi, which has a leg on A and a leg on A complement, is very, very close to the state that I get by taking psi epsilon, adding one inclusion map on one side and adding the other inclusion map on the other side. And this, if I draw my original picture over it, is exactly what I said I wanted. It's a tensor network where the bond dimension of the leg that crosses the minimal surface is e to the area over 4g Newton plus subleading corrections. And this, in sort of this picture as I've drawn it, and this answers one of the other questions that was asked earlier, you can sort of explicitly see that these two inclusion maps, V and W, correspond to each entanglement wedge, right? The map V is something that pushes one of the entanglement wedges through, or sorry, it pushes the entanglement through one of the entanglement wedges to the boundary, and the other map, W, pushes the state through to the complement, through the complementary entanglement wedge. So this is all I'm going to say specifically about this paper. I think that, well, like I said, if you look at the paper that we wrote, you can see the generalizations of this. You can see that you can go inductively and build up any number of non-crossing Ryutaki-Nagy surfaces using this prescription. But I think that the lesson that we're learning from this is fundamentally, like I stressed before, that the Ryutaki-Nagy formula tells us that holographic states can be efficiently simulated on significantly smaller Hilbert spaces. Hilbert spaces whose dimensions are controlled by the entropy. And I think that this is a hint of an idea that many people have been discussing recently, and I think was really pioneered by Mark van Ramsdonk, which is that we should think of entanglement as being the thing that holds space-time together. And one way that we see that is that entanglement is the thing that controls the size of the Hilbert space that our state really lives in. So that's all I want to say about this paper. I do want to talk about Outlook. I know we're coming up on time, although we did start a little late, so I'd like to ask the organizers if I should continue or stop here for questions.
I think it would be a good time for some questions. Although we already had. Okay, so Matt Hedrick has the question.
Oh, hi, Matt.
Hi, John. Very nice talk. Thank you. First of all, can you hear me?
Yes, I can hear you.
Great. Actually, I have a few questions. I don't want to hog the time. Well, one of my questions is I wanted to know what your outlook was going to be. But let me first ask like a very narrow question. So if you have multiple regions, like you started with A, B, and C and so on, but you assume non-crossing RT surfaces, the tensor network you end up with is a tree, is that correct?
Yeah, it's always going to be a tree.
Okay.
Yeah, you don't get loops if you don't have crossing networks or crossing surfaces. Okay.
I just wanted to clarify that. But then another question I have, which is a little bit broader, is, you know, it's sort of been well understood for a long time that the classical limit of gravity is in some sense a thermodynamic limit, and the large N limit of, you know, gauge theories is that you have in holography is also some kind of thermodynamic limit, where instead of having, you know, a large number of particles or a large volume like you normally do in textbook thermodynamic limits, you have the large N limit instead, and that you know, the behavior of entanglement entropies sort of reflects that. So my question is, did anything you tell us today, would anything you told us today change if everywhere I replaced the word holographic with thermodynamic, and everywhere I replaced 1 over g Newton with N, where N is some, you know, number of particles or something like that, that I'm taking large in a conventional textbook thermodynamic limit?
No, it wouldn't. So yeah, so the important thing for this saddle point calculation is just that the matrix moments scale extensively in some parameter that I take the limit of. So if my Rényi entropies all scale with N, as they often would in a thermodynamic system, everything I said today is still going to be true. Now, so, there are parts of the paper that I didn't talk about today that are more specific to quantum gravity. If you want to consider crossing RT surfaces, then you are going to need to appeal to things like the entanglement of purification conjecture, which is not something that holds in a generic thermodynamic system. I didn't talk about that just for lack of time. I do think it's important to remember that most of what I've said today is true of generic large N systems, as you suggested.
I see. Okay, so at that level, the observation is that you can represent a thermodynamic system that you've divided up into subsystems by a tree tensor network.
Yeah, exactly.
Okay.
Yeah.
Okay.
So long as the subsystems are nested in the right way, so that they give you a tree structure. Yeah.
Right. So it seems like it seems like the if we're looking for what's special about quantum gravity that goes beyond it just being because not every thermodynamic system is gravity.
Exactly.
Right? I mean, a weakly
Right.
coupled large N gauge theory is not gravity in the
Right.
in the normal sense. So if we're trying to understand what's special about gravity, then we need something a little more sort of fine-grained.
Yeah, that's exactly right. And it's something that we tried to approach in this paper by using the entanglement of purification. I'm not personally sure how much I believe in the entanglement of purification right now, which is one of the reasons I didn't talk about it. But I do think that if you sort of, well, if you think about things like entanglement of purification or the surface state correspondence, those really are special to quantum gravity, and you can use those to subdivide these networks further and get something that is more gravitational.
I see. Okay. Okay.
Yeah.
I don't want to hog the question period, but I would like to hear about your outlook.
Yeah, I'll certainly will talk about that, even if we, let people who want to leave before then. Any other questions before I maybe talk a little bit about outlook? We did get started 5 or 10 minutes late, so I don't feel too bad about going a little over. Okay, so maybe I'll talk about outlook. I certainly won't be offended if anyone decides to leave now, although I think this is really the interesting part of the talk, so I hope you stay. I'm going to talk a little bit about what I think are from my perspective, the most interesting recent developments in the tensor network literature and the most interesting directions for future work. So the way I'm going to frame this, like I said at the beginning, is what are tensor networks good for? Because I think that we as physicists sometimes have a bad habit of finding a model we like and starting to answer questions exclusively about the model while forgetting the theory we're really trying to explain. So I think it's good to sort of keep in mind, what are the questions we want to answer about quantum gravity, and how can we use tensor networks to approach them? So I'll talk about two sort of ideas here. And the first one is random tensor networks. And I said at the beginning that I would come back to these. I think random tensor networks are really great. If you had asked me this a few months ago, I had not yet been, I guess, proselytized to about random tensor networks, but some conversations that I especially want to credit Tom Faulkner and Chris Akers with have changed my point of view. So randomness in quantum gravity has a long history. Probably the first sort of real major development along this line was due to Don Page, who used random states to sort of give some intuition for how we should think about the development of entropy in black hole evaporation. And then more recently, there's this very famous work by Patrick Hayden and John Preskill, where they talked about random unitaries, and they used that as a model for black hole evaporation, and we learned a lot from that. So both of these concern black hole evaporation. The first from Don Page involved these random states. The second from Hayden and Preskill involved these random unitaries, these random dynamics. And then there's this recent paper, the one that introduced random tensor networks it has 6 or 7 authors. I'm afraid I can't name them all. This is the random tensor network paper. And the way I would view it sort of philosophically is that what they effectively did was they took this simple random model, where I had a single random state or a single random unitary, and they graduated it so we could start thinking about random geometries, thinking about these tensor networks as discrete geometries that had some information theoretic randomness in them. And what they found is that they were able to accurately reproduce the Ryutaki-Nanki entropies in these random tensor networks. So I think that these methods have a long history, and I think that they are promising going forward. And one of the big reasons that they're promising is because of a recent development that came about a year ago, using this idea of fixed area states. So fixed area states were introduced by 2 sets of authors at the same time. The one set of authors whose perspective is the one that I think is most common now is Shi Dong, Daniel Harlow, and Don Maroff. But at the same time, Chris Akers and Pratik Rath considered some very similar ideas in quantum error correction that I think come with their own quite interesting intuition. So the basic idea of a fixed area state is that suppose I have some space-time g mu nu, which is secretly a quantum state, under the hood, and I have a surface gamma. Now, the area of a surface gamma fluctuates. It fluctuates due to quantum corrections. On the most basic level, you can see this due to like graviton fluctuations that cause some fluctuation in the area of the surface. So if I take this state and I project onto eigenvalues of the area operator, the operator whose expectation value gives the area of that surface, I get something called a fixed area state. Now, a fixed area state is not geometric. We actually talk about that quite a lot in the paper that most of this talk was about, the paper with Ning and Jeff and Aaron. A fixed area state is not a geometric state. It doesn't actually properly preserve the covariant geometry of the spacetime, but it's a state that has some interesting properties. And in particular, the properties of this state, of this fixed area state, are well reproduced by random tensor networks. Now, to explain that, I need to tell you something that I didn't tell you before, which is that while random tensor networks do a very good job of reproducing the Ryutaki-Yanagi entropies, they don't do a very good job of reproducing the other Rényi entropies. They give the wrong answer for the other Rényi entropies, but they give the right answer for the Rényi entropies of fixed area states. So it seems, and this was I think what was really stressed by Dong, Harlow, and Merolf, that random tensor networks give quite good models of the properties of these fixed area states. So here's a formula that I think is a very good way to go about research projects. So suppose there's some quantity in quantum gravity that you want to understand in geometric states. I'll give an example of this at the end. But let's say there's some general quantity in quantum gravity that you want to understand in a geometric state. But it's too hard in the geometric state, so you decide to start in these fixed area states. And by integrating over enough fixed area states, you can reproduce a generic geometric state. So it's not too bad of an idea to start in this sort of simplified eigenspace, the eigenspace of the area operator. But perhaps even the fixed area states are too hard, so you want to start by modeling them with a random tensor network. I think this is a very, very promising way to go about a generic research program, is to use these random tensor networks as a model for fixed area states, which are themselves sort of a component of the full geometric state. And with that in mind, I want to plug some work that's currently being done. I know that at least two of the authors on this forthcoming paper are Chris Akers and Tom Faulkner. I believe that Pratik Rath might be involved, as well as one of Tom Faulkner's students, although I'm afraid I don't know that student's name, so I'm sorry for not crediting them properly. But there's interesting work in this that follows exactly this formula, where they're trying to study this quantity called the reflected entropy. The reflected entropy has recently become very interesting. It was discovered by Dutta and Faulkner to be an interesting holographic quantity. And in order to try to understand that quantity better, they're following exactly this model. They're starting in the fixed area states, which they're modeling by random tensor networks. And I think that there's a lot of room for exploration here. The other sort of good open direction is to continue to use tensor networks for encoding intuition. Now, this is how tensor networks, I think, really sort of took off, was that we were able to use them to understand the idea of how the bulk is encoded in the boundary in quantum gravity. This is, you know, a really big question. This bulk state must somehow be encoded in the boundary state, but the actual details of how it's encoded can be pretty fuzzy. The program of understanding this often goes by the name entanglement wedge reconstruction. So the basic idea of how sort of the encoding intuition started was noting that if I had some tensor network that, you know, has some interior and goes out to the boundary, and then I add some internal legs, if I have a tensor in the interior that has some internal legs, then I can view the tensor network as being a map from the red legs to the black legs, from sort of the bulk to the boundary. And we can use ideas like this to build intuition for bulk to boundary encoding. And I want to give a really, really great recent example of how this, this intuition was used to learn some very interesting things about quantum gravity. And this paper goes by the name of the Python's Lunch. It is joint work by Adam Brown, Frank Garibian, Jeff Pennington, and Lenny Suskind. And I'll give a very, very brief overview. It's a good paper. It's worth reading. The idea is, imagine I have some tensor network that has some thick piece, some piece that's very wide, that then narrows to a very thin piece, and then spreads out again. And suppose furthermore that I have, say, one internal leg on this tensor network that is outside of the thinned region and one that's inside of the thinned region. And suppose that I, have access to the state here on the boundary, and I want to find out information about these two internal legs. Let's say, for example, I act with an operator O1 over here and an operator O2 over here. And I want to be able to say, find out which operators I acted with, starting with the state on the boundary. Now, in principle, sort of the most natural way to try to do this is to undo the tensor network that produced the state. I said at the very beginning that I was going to assume that every tensor was either a unitary or an isometry. So let's say that, these three tensors on the right are all unitaries. I can just undo them very easily by applying the inverses of those unitaries. And by doing that, I can get back to the O2 leg and I can figure out what was there. This unitary here, this tensor here is an isometry. It splits from a small number of legs to a large number of legs. And an isometry is also easy to undo. But this tensor here is very hard to undo. It's a projection, right? It takes a large number of legs and takes it to a small number of legs. And projections are in general very hard to undo with any kind of computational efficiency. So what they talked about in this paper was how if you have a tensor network like this, it's always going to be much harder to figure out what happened at O1 than it is at O2. So I'll say O1 harder than O2. If I think about these tensor networks as representing some space-time geometry, then this translates to a geometric problem. And what it basically says is that if I have some geometry that has a wide region and then a narrow region, it's going to be harder to access things behind the narrow region than it is things that are in front of the narrow region. One great example of this is a black hole. And that's the chief example that they take in this paper. You can sort of imagine that this narrow region is the horizon of the black hole at late times. And the interior, the thick region, is this, the wormhole behind the horizon that grows at late times. And they've used this sort of picture to get some understanding as to why it's so hard to reconstruct information behind the horizon and relatively easy to reconstruct information in front of the horizon. So I think this is a really great paper. I encourage you to read it. And I think that this is a really promising future direction to use tensor networks to understand sort of geometric obstructions to this, this encoding problem. And with that, that's all I want to say. That's the extent of my outlook. I really would like to thank you all for your attention, and I'm happy to take questions.
Okay, thank you very much. John, that was a great talk. So we have some time for questions.
So just a quick question. So the starting point for your talk was a work by Brian Swingle who talked about Mera tensor network and the relation to hyperbolic disk geometry. And one and a half years ago, Guipre Vidal had papers like trying to understand Mera more geometrically. Does your work shed some light on this long-standing question of the interpretation of Mera in holography, or that's sort of perpendicular to what you did?
I would say it's kind of perpendicular. I do think that's a very interesting question. So sort of by my view, Mera is kind of a good way of thinking about the vacuum state of ADS-CFT, because the vacuum state just has this very simple hyperbolic geometry, and Mera has, this hyperbolic geometry. It starts with a small number of nodes and spreads out exponentially to a large number of nodes. And I think Brian's chief insight was this encoding intuition question, was that we could think of Mira as encoding the bulk into the boundary. There's really great work by Isaac Kim and perhaps Michael Castoriano, where they showed that Mira is in fact a quantum error correcting code in the way that you would hope it would be for it to be holographic. I would say my personal perspective is that we've graduated beyond Mira. And that's not to say there aren't still interesting questions involving Mira. I think Guy Vidal, for example, you mentioned, has, with collaborators, done some very interesting work on Mira in recent years. But I would say that this is, Mira is one part of the question. And what we've tried to do, not just myself, but many other authors in recent years, we've tried to really expand our understanding of tensor networks beyond Mira. I mean, this Python's lunch question, for example, is not the kind of thing that would show up in any Mira tensor network. So I would say, yeah, my perspective is that we should look beyond Mira, not just try to understand Mira better.
Yeah, thanks.
More questions?
Well, I mean, if nobody has any other questions, I have one more. So
yeah, go ahead.
Do you have, I mean, does your work shed some light on entanglement shadows, or this is also like beyond the scope?
Yeah, so this is, so the more speculative part of the work does. So I'll just say a few words about this. If the part of the paper where we talk about entanglement of purification said, like, suppose I have some, intersecting grid of extremal surfaces. We use the entanglement of purification conjecture to sort of build up a tensor network for this grid by first building up a tensor network for this top layer, and then building up a tensor network for the second layer from that, and then going on inductively. And there were obstructions that we ran into while doing this iterative procedure, geometric obstructions in the space-time that could stop you from going forward and building up a network like this constructively. But it's been over a year, but as I recall, one of the things we said in the paper was that doing this kind of iterative procedure, if it worked, could get you behind entanglement shadows. And sort of the point of that is that entanglement shadows are boundary obstructions, right? They are regions that you can't reach with extremal surfaces anchored to the boundary. But if you do some sort of iterative procedure where you start with some extremal surface and then you jump off of that extremal surface with other extremal surfaces, then you can possibly use that kind of iterative procedure to get behind entanglement shadows. And I do want to say that that idea had been previously mentioned in a paper by Yasunori Nomura, and I'm afraid I forget who his collaborator was. It may have been Pratik, it may have been someone else. But it's cited in our paper, so you can go and look at that if you're curious.
Thanks.
Okay, well,
if
thank you,
there's
everyone.
more questions, let's thank Jon again.
Thank you, everyone. It's good to see you all, at least virtually. Have a great day.